Hello viewers, today I am going to talk about something which is very exciting for the entire physics community, and namely it is the direct detection of ripples of space-time geometry that was predicted almost about 100 years back by Albert Einstein. As you know, what Einstein did was to make a consistent theory of gravitation that is consistent with his special theory of relativity. And this theory of gravity, which is completely consistent with special theory of relativity, is called the general theory of relativity. Today in my talk, I am going to cover the following topics concerning gravitational waves. First, I will give a brief introduction to special theory of relativity and what are its basic tenets. Second, I am going to talk about how Einstein, using the experiments performed 400 years back by Galileo, how he developed the entire relativistic theory of gravitation based on certain insights. Third, I am going to talk about certain predictions of general theory of relativity like black holes and gravitational waves, and finally, I will talk about gravitational waves, its indirect detection, and finally, the direct detection that happened on 14th September 2015, but this event, after several analysis making sure, was not a false alarm when finally all the 1,000 and odd authors of the paper were convinced that it is a real signal. They announced it on 11th February 2016. Good. So, now let us go ahead with the subject of gravitational waves, which is nothing but we can say it is sound of gravity. On February 11th 2016, the LIGO community, they announced the result that they had seen an event on 14th September 2015 that corresponds to emission of gravitational waves by two inspiraling or merging massive black holes. So, in this picture you can see that a big black hole and a smaller black hole, they are going around the common center of mass, and because of Einstein's prediction, whenever there is asymmetric change in the matter distribution, they will generate gravitational waves, and these gravitational waves will carry away energy, and therefore, the binary system has to merge into one single unit. Albert Einstein, he was of course responsible for 5 major breakthroughs in physics at the turn of the 20th century, like special relativity, photoelectric effect, Brownian motion, general relativity, and some foundational aspects of quantum mechanics. Before I actually get into the nitty-gritties of general relativity and gravitational waves, let me also mention that there is a whole Indigo consortium in our country that involves several institutes and universities like Tata Institute of Fundamental Research, Raman Research Institute, Inter-University Centre for Astronomy and Astrophysics, various IISERs, IITs and universities. Delhi University is also part of this Indigo consortium, and this Indigo consortium is participating in research in the field of gravitational waves as well as disseminating pedagogical lectures so that young people can be trained in this field. The detector, which is essentially an interferometric detector, has been set up already in several countries like USA, France, Germany. Now, There is going to be one such interferometer in India. That project has been christened as LIGO India, and it is going to be very exciting time for young students to jump into this field and conduct research, because the experiment is going to use cutting edge physics tools like quantum states of light, which is called squeeze states of light, fantastic vacuum, excellent seismic screening of hanging mirrors, fantastic optical elements that are going to be used in this experiment. Of course, apart from laser interferometric detectors, there are also resonant bar detectors to detect very narrow band gravitational waves. So, let us begin with some introduction to what we see and how we interpret the data. So, we know that entire events in this physical world that used to be thought as happening in a fixed space time background arena. So, as though the space time itself acted like a huge colosseum or amphitheater where matter played their own action, and information from various matter distribution came to the sensors, or what you can say as measuring apparatus designed by human beings, in the form of electromagnetic signals or any other signal that can be used to interpret data. And earlier physicists used to believe that it is the matter which changes with time, their distribution goes on evolving with time. The space time acted as a given arena, but all that changed with general theory of relativity, when Einstein showed that space time itself is dynamical. Whenever matter distribution changes with time, the space time geometry itself changes with time. So, as though you are having a play where not only actors act out, but depending upon the acting meted out by the actors, the stage itself keeps changing. The stage also dances with the acting of the actors. That is the kind of revolution which general relativity brought about. The matter itself is organized in various structures. So, at the smallest, we know that there are so called theoretical modeling called strings, and it is believed that all other elementary particles are excitation of tiny strings, tiny meaning they are almost of the size 10 raised to the minus 33 centimeter, and the excitation, various modes of excitation of the strings, they appear as either electron or quark or neutrinos or what have you. But of course, string theory is still a theoretical model. We still do not know whether it is the correct theory, because it is very difficult at this energy scales to test the predictions of string theory. However, the high energy physics, we know that the electroweak unification, which talks about how weak interactions are unified with electromagnetic interactions, all those have been tested to very good precision. So, similarly, strong interaction, which is given by the theory of quantum chromodynamics, has also been tested to great accuracy with accelerator experiments like the Large Hadronic Collider experiments. If you go above, then you know that the elementary particles are organized in the form of atoms, molecules, and finally, these molecules, they give rise to complex macromolecules like DNA, RNA, amino acids, and essentially they lead up to living cells and living systems, and over almost 1,000 million years of evolution, the primates came into the scene, and the apex of this evolution was human beings themselves with their great power of thinking. Now, the same objects, namely the human beings who are made out of all these fundamental particles, they themselves are trying to understand the nature of the fundamental particles as well as the structures beyond, because on scales slightly bigger like Earth scale, planet scale, where gravity starts dominating, there you have mostly it is the classical physics of gravitation that determines the fate of stars, galaxies, clusters of galaxies, superclusters, voids, great wall, etc. So, here is a peep into the universe. This is a picture taken by the Hubble Space Telescope, and at large scale the universe is known to be inhabited mostly by galaxies. So, the galaxies, each of these oval shaped objects, they essentially contain more than 10 to the power 10 stars, and our Milky Way itself is a galaxy, and solar system is just a part of our Milky Way. So, just like cells are the basic building block of living systems, it is the galaxies which are the building block of the entire cosmos. Now, let us slowly go into Einstein's theory of relativity. Of course, I am only going to talk about the salient features, not the gory mathematical details. What we know is that in this classical world, what we see are events. So, for example, I am speaking, but I am speaking from a particular position at a particular time. So, if you want to precisely fix the event of my lecture, you have to tell me where I am and at what time I am speaking. So, our physical world can be thought of as a collection of events, and each event has to be specified 3 spatial coordinates and 1 time coordinate, and therefore, the world of events is essentially a 4-dimensional world, the 3-dimensional space plus 1-dimensional time. And then what Einstein, using his great physical insight, what he did was he realized that speed of light in all inertial frame of reference is fixed. Whether in your frame of reference a source of light is moving towards you, or whether the source of light is somewhere there and you are moving towards the source of light, if you measure the speed of light in your inertial frame, the speed of light is going to be exactly 3 into 10 to the power 8 meters per second, which is completely counterintuitive. That does not happen for any other speed. So, for example, if a train is moving with respect to you at a speed of 20 kilometers per second when you are at rest in the platform, if your friend is sitting in the train, in your friend's frame, the train has 0 velocity. So, that was a counterintuitive point which would have baffled everyone, but Einstein took a bold step. Assuming this, he got whole lot of new predictions like mass and energy is equivalent, so that anything that has mass m has energy E equal to mc square, and so on. Similarly, he proved that 2 events which happen at 2 different spatial points, if they happen to be happening at the same time for me, a friend who is moving with respect to me will find that the 2 events are not simultaneous. So, in other words, simultaneity is not absolute. 2 events which are simultaneous to me need not be simultaneous to other people. In other words, he showed that time, flow of time depends upon inertial observers. Newton believed that the flow of time is universal for everyone, but Einstein came and completely shook the world by saying time itself is relative. In other words, he showed that if I am in a frame of reference with my spatial coordinates x, y, z and time coordinate t, and if a friend of mine is moving with some speed with respect to me, then he will find that his time coordinate is mixed up with my time and space coordinate. So, time also gets transformed. Then what he showed was that no object which has non-zero rest mass can ever move with speed c, and furthermore, no object can move even faster than the speed c, whose value is 3 into 10 to the power 8 meters per second, or you can say 3 into 10 to the power 10 centimeters per second. That came out of his theory completely, and that meant that there cannot be any perfect rigid body. That means, if you have a long rod, you might think it is rigid, but it cannot be perfectly rigid. Why? Because if you tap at one end and if it is perfectly rigid, then if you push one end, the other end at the same instant must move. But then with that you can send energy with infinite speed, but that is not possible in relativity. So, in other words, what Einstein showed was nothing can be perfectly rigid body. If you tap at one end, then this disturbance will propagate with a speed less than the speed of light till it reaches the other end, then the other end will move. And as I said, from his special theory of relativity, it came out that energy and mass are equivalent. That means, anything that has energy E has mass E divided by c square, anything that has mass m has energy mc square, both are equivalent. Similarly, what he showed was that if you have a rod of some length, let us say I take a meter rod, meter stick, then if my friend moves with respect to me with speed v, then my friend will measure my meter rod does not have a length of 1 meter, rather it has the length 1 meter multiplied by square root of 1 minus v square by c square. That means, for him the length is contracted. Similarly, he will find that my clock is not ticking with a rate 1 second, rather he will say that my clock is going slow, in the sense that when his clock ticks by 1 second, my clock has not at all ticked. So, time dilation and length contraction came out of special theory of relativity. So, in other words, my talk, which is for 40 minutes, so if you find that it is not 40 minutes, but 2 hours, all you can say is that you are moving away fast with respect to me. So, that is why my time is getting dilated for you. So, time and space came about completely in a different manner when Einstein gave his special theory of relativity. Next, Einstein knew that Newton's gravity cannot be the last word. How did he realize that? Newton said that if you have two objects, one with mass m1 and the other with mass m2, and if the instantaneous distance between them is d, then according to Newton, the mutual gravitational attractive force between m1 and m2 is minus gm1 m2 divided by d square. But then if this law is correct, if one mass moves right now by certain amount, then according to Newton, the other mass will start immediately feeling the force, because the force depends upon the instantaneous distance. But Einstein showed nothing can move faster than the speed of light. So, instantaneous transmission of change of position cannot hold good, and therefore, Newton's gravity cannot be correct. And Einstein worked for 10 years from 1905 to 1915 to give a relativistic version of gravitation. And how did he go about it? The basic physical insight he used is the 400 years old experiment conducted by Galileo from the Leaning Tower of Pisa. The celebrated story is that Galileo wanted to disprove the old Aristotelian law. The Greek philosopher Aristotle around 300 BC had claimed that heavier objects fell towards the earth at a faster rate. But Galileo, of course, being the father of physics and being a very good experimentalist, knowing how to measure quantities accurately, knew that Aristotle was wrong. But all the established religious systems like church, etc., they all believed in Aristotelian viewpoint. So, they refused to believe Galileo. So, what did Galileo do? Like a true experimental physicist, he took two massive objects, let us say 10 kilogram shot put and another 30 kilogram shot put. He climbed up to the top of the Leaning Tower of Pisa, and at the same instant he released the 10 kilogram and 30 kilogram objects, and lo and behold, both the two objects, they reached the ground at the same time, proving that the rate at which objects fell to the ground is identical. They do not depend upon the masses of objects. This is called the Galilean equivalence principle. What Einstein did was, he used this principle in a fantastic, completely original insight. So, that is what I am going to illustrate to you. What Galileo showed was that the gravitational charge or gravitational mass is exactly equal to inertial mass, because if objects are falling to the ground at the same rate, then it was Newton who showed that gravitational mass must be equal to inertial mass, because according to Newton's first law of motion, force is equal to mass times acceleration. But then Newtonian gravity said that if you have two objects m1, m2, then the attractive force is equal to minus gm1 m2 divided by d square, but m1 a equal to minus gm1 m2 by d square tells you m1 gets cancelled and acceleration does not depend upon m1. That means gravitational mass m1 is same as inertial mass m1. So, this is what Newton had deduced. Of course, even today such fine experiments are being conducted to see whether indeed inertial mass and gravitational mass are identical. Various groups are doing the experiments, starting from Yotovos to even fine experiments conducted 20 years back by the Gauri-Budnoor experimental group at TIFR. Now, Einstein, what he did was, he used this Galilean equivalence principle and realized something strange that happens with gravity. What he showed was that if you have a frame of reference that is freely falling under the action of gravity, then the gravitational force simply disappears. In fact, he had claimed that when he realized this, that was the happiest day of his life. What is happening is that, imagine that I am having all kinds of gravitational experimental kits with me, like a simple pendulum which I can hold the end of the string at one point and release the bob, so that the bob executes simple harmonic motion. By the time period I can measure the acceleration due to gravity, etc. And I have many such experimental implements with me, and I am, let us say, at the moment in a lift in a very tall storied building. I am on the top floor and I have just entered the lift, and when the lift is not moving, I carry out all kinds of experiments. I find that the gravitational constant, the gravitational acceleration due to Earth's gravity is very close to 9.8 meter per second square. That I know by doing the experiments. But heaven forbid, one accident takes place. What happens is, the cable of this lift snaps, and let us assume that the lift in which I am standing, that lift freely falls under gravity. So, it accelerates downwards towards the surface of the earth with acceleration 9.8 meters per second square. Now, if I do experiment in my freely falling lift, I will find gravity has disappeared. Why is it so? If the lift was made of complete glass doors, what will you see? You will see that I am freely falling. All the objects that I release, they are also all freely falling with the same acceleration. That is what Galileo had showed us. In other words, therefore, he will conclude that I, being trapped in the lift, I do not find any relative acceleration between any object, and that is what I find too. I find that in my frame of reference, there is no acceleration due to gravity. Gravity has completely disappeared. That means, if I throw a ball with some initial velocity 10 centimeters per second, in my freely falling frame I will find that object is moving just straight. but my friend who is outside, he can see that that object will take a parabolic trajectory. But he knows the reason I say it straight is because I am also accelerating downwards just like that small ball, and therefore, I find there is no acceleration and I find the ball to be moving straight. Equivalently, this entire so called Einsteinian equivalence principle can also be stated in a different way. Supposing I have a frame, I am inside the frame which is resting on the earth, and I do all kinds of experiment. I drop an object, we know that the object will fall towards the surface of the earth with acceleration g, which is 9.8 meter per second square. Consider my friend who is very far away from all known objects. Since he is very far away from all known objects, in his spacecraft there is no gravity. Supposing due to some reason his rocket gets accidentally fired, so that his rocket starts moving upward with an acceleration a, which is exactly 9.8 meter per second square. Then he will think that suddenly someone has switched on gravity like Earth's gravity, g equal to 9.8 meter per second square. If he does any experiment, he will find that is exactly like the gravity. So, in other words, an accelerating frame without a real gravity acts as though there is uniform gravity, while in a gravitational field, if I freely fall, then gravity disappears. Both are equivalent, and this immediately tells us some amazing consequences. And what is that? Supposing you have a lift and the lift is accelerating upwards with an acceleration a. Then if a lady does some experiment, like supposing she was initially holding a ball and she gives an initial velocity of 10 centimeters per second, let us say, but if the lift was to begin with in no gravity situation, she was in space, then I, who is outside the lift, because I am also in space, no gravity, I find that when she gives the ball a velocity 10 centimeters per second, the ball, according to me, because there is no gravity, the ball simply moves straight. Newton's first law. Without any force, an object continues to be at rest or continues to move with uniform motion. But what will she see? She is accelerating upwards, so she will find that the ball continues to fall towards the floor. Why? Because her frame is moving upwards with greater and greater speed, and therefore, the distance between the ball and the floor will keep on decreasing, because the frame itself is accelerating upwards. And in fact, as I mentioned, she can do any experiment and she will find as though there is a uniform gravity with gravitational acceleration whose value is minus a, pointing downwards. So, this is what Einstein's reasoning gives us. Now, we can ask, can we predict something new? Because science is all about predicting something new, and if that new prediction is corroborated by experiments, then you know your theory is correct. So, Einstein immediately realized if this is correct, then you can do the following experiment. Supposing she holds a torch in her hand and points it horizontally and switches on the light. What will I see? I say that there is no gravity, and when she switched on the light will simply move horizontally like this. From here, the light beam will just go straight. But what will she see? If her acceleration upwards is very high, she does not know that the frame is accelerating. All she knows is there is a gravity, because acceleration is equivalent to gravity, as we have seen earlier. So, therefore, she will see, according to her, in this frame where there is gravity, the light beam will bend towards, just like the ball released took a parabolic path, the light beam will start falling towards the floor. Of course, to do this experiment, the acceleration must be huge, because light moves with a great speed. In other words, what Einstein said, that this gravity cannot be distinguished from real gravity, and therefore, when light goes near a massive object, the gravity of the massive object will cause bending of the light beam. So, this is what Einstein predicted, that supposing you have a star very far away, and let us say the star was visible when the earth was on this side. We know that earth is going around the sun. So, when earth, let us say this is the winter part, December, in December you could see the star here, the real position of the star is here. So, supposing you try to see the star during the summer, but you have to somehow obstruct the sun's glaring light, and such a thing can happen if moon comes between earth and sun, which is a total solar eclipse. So, wait for a total solar eclipse, so that the sun's light gets completely obscured by the moon in between, and then you can see the star and then measure its position. You will find that the apparent position will be different. Why? Because according to bending of light, the light from the star as it comes towards the earth will bend. So, therefore, when it reaches you, what will you think is the apparent position? You have to just draw a tangent to this curve. You will think that the apparent position is this. So, during the solar eclipse, when you see the star, you will see the star here, but the actual position is this, and this difference Einstein calculated and predicted, which is about 1.75 arc second. 1 arc second is 1 degree divided by 3600. So, it is a very tiny number, and indeed in 1919 Eddington and his group of astronomers saw exactly what Einstein had predicted. So, therefore, it was corroborated that indeed general relativity seems to be correct, but according to general relativity, gravity is not a force at all. What general relativity said was gravity is nothing but manifestation of the geometry, non-Euclidean geometry of the space time. Just like this is only an analogy, do not take it seriously. Supposing you have a two-dimensional stretched out rubber sheet, then when there is no heavy object, the rubber sheet is flat, Euclidean geometry is correct. But now if you put a heavy object, it immediately makes the rubber sheet sag, and now the geometry of the two-dimensional rubber sheet is no longer Euclidean. If you draw a triangle, then the sum of the interior angles of this triangle will no longer be 180 degree. If you draw a heavier object, it will make the entire rubber sheet bend more. And the bending of light Einstein explained in a geometrical way. He said the bending of light is not due to any gravitational force. What is happening is, because there is a massive object, the straightest possible line in this curved geometry is not this straight line, but a bent line. That is what is the straightest possible line, and so therefore, there is not real force, but it is the geometrical effect which is causing apparent gravitational force. So, this is another picture with which I can illustrate. We know from Euclid's geometry, if you take a two-dimensional surface, then you can have two stars, and light emitted from the two stars can come to you as parallel rays. But what happens is that our space time, because of matter, the matter curves the geometry of the space time. So, supposing the curvature of this two-dimensional world is not flat like Euclidean geometry, but it is like the surface of the sphere. Now, you see the straightest possible line on the surface of the sphere you can show are elements or chords of the great circle, and as you know, no two great circle can ever remain parallel. If you extend it, they will finally meet. For example, the longitudes on earth, they meet at the north pole and south pole. So, straightest possible lines on the surface of the sphere, you cannot have ever parallel lines. Such a system of geometry has a positive geometrical curvature. Similarly, you can think of the horse saddle, the surface whose geometry is like the horse saddle, that has negative curvature. This horse saddle, the peculiar thing is, in one direction if you come, there is a valley, that means there is a minimum point, but in another direction there is a maximum. In this direction this point is maximum, in the other direction it is a minimum. Such a surface you can show has a negative curvature. In other words, Here if you take two straightest possible line, you extend it, they will diverge from each other. Similarly, if you draw a triangle on this surface, then the sum of the interior angles of the triangle will be less than 180 degrees, while on the positive curvature surface, if you draw a triangle, the sum of the interior angles will be more than 180 degrees. You might ask, but where is the connection between equivalence principle and gravity which we discussed and the whole idea of geometry? And that was the beautiful point which Einstein realized. Consider a mathematician who deals with geometry. Supposing he encounters a two-dimensional surface like this surface of the ball. He wants to do geometry. How would he do? He is very difficult because all he knows is Euclidean geometry, but then he is a clever mathematician. What he will do is he will cut out a small patch on this curved surface. The small patch, if you draw, here is a small patch, if you at this point if you draw a tangent plane, the small patch is very much like tangent plane, and geometry on the tangent plane is exactly Euclidean geometry. That means the geometry on the small patch is exactly Euclidean. In other words, this small patch is like our freely falling frame where gravity disappears. Just like the small patch, the geometry is exactly like Euclidean. So Einstein immediately made a connection, just like in a freely falling frame gravity disappears and all special relativity applies in a freely falling frame. Similarly, in a geometrical, any arbitrary curved geometry, if you take a small section, there you will never notice the non-Euclidean geometry. The geometry is perfectly Euclidean. And then Einstein made this connection between gravity and geometry using the mathematical theory of tensor calculus. In other words, to learn general theory of relativity, one has to learn the tensor calculus thoroughly, so that one can grasp the nitty-gritty of general theory of relativity. So Einstein, what he showed was gravity is nothing but a manifestation of the non-Euclidean geometrical nature of the space and time. So general relativity predicted many things. Apart from bending of light, you can show that if you shine a beam of light upwards, then as the light goes upwards, the wavelength of the light keeps getting elongated. That means if you send blue light, as it goes upward, it becomes red light. Similarly, if matter distribution changes asymmetrically, they cause emission of gravitational waves. Similarly, he showed, or rather very soon Schwarzschild got a very interesting solution as soon as Einstein gave his general theory of relativity, and from that solution it turned out that if you take a massive object and compress the mass below a particular region, then it turns into a black hole where the entire matter collapses to a single point. Similarly, general relativity, Einstein did not know it, but from general relativity one could have predicted the Big Bang model for the universe. Today we know that the universe is expanding, and this expanding solutions, mathematicians like Friedman and general relativists like the Belgian general relativist Georges Lemaitre, they had worked out solutions which said from general relativity you can have expanding universe. In fact, Georges Lemaitre had predicted that our universe is an expanding universe. Unfortunately, his paper was in French. Many people did not realize till Hubble, using experimental observation of galaxies, showed that the universe is indeed expanding. So general relativity predicts two very drastic events. One is formation of black hole, the other is gravitational waves. It turned out that the September 14th event of 2015 corroborated not only gravitational waves, but also to a great degree black holes. I will stop now at this point. In the next segment of the lecture, I will deal with gravitational waves alone.